You all don't know is this is like take number 4. These take forever because I don't know how to edit videos. So if I totally screw up, which you guys know I'm very likely to do, then I have to kind of start my whole video all over from scratch. So hopefully this one will work. If not, I'm just going to cry. Okay, so on one of the last videos, we did example number 3, finding internal forces and moments using positive beam notation. And I have that piece of paper right here. This is what I'm kind of looking at. And so this time what we're going to do is we want to find shear moment equations to represent the forces as they're changing down the length of the beam. So before we cut it at 3 meters, we looked at it from the left. We found internal forces. This time we need to kind of do the similar thing, except we're going to write equations. Again, we come from the left to the right every single time. X always is starting at the left, going to the right, and luckily this time we only have one segment of beam, but I kind of wanted to show you how you take care of loads applied like this. So I do know that I have 800 newtons as a reaction, and I'm going to kind of draw a dotted in representation of those loads. So there probably is a fancy equation finding the centroid blah blah of whatever shape this is, the rhomboid, trapezoid, I don't know. But that just seems like a lot of work when I know how to find areas and centroids of triangles and rectangles. So our first area is rectangular, and we know that it's going to be a base times a height, and that the centroid acts through the center. Our second area is up here, and whoops, we know that it's triangular, which has a 1/3, 2/3. The 1/3 comes back from that right angle end where we have more area. Remember, the centroid is where we could balance it on our finger and it would balance. Okay, so that's why the centroid is back towards this more area. So this one's pretty easy. I know that this is going to be 200 newtons per meter, but now I have to deal with that triangular portion. If I'm looking back over here, as I go from 0 to 6 meters, I'm going from 0 to 200 newtons per meter at the top of this triangle. Remember, we talked about that last time, that the 200 we have to take off. So instead of 400 for my height, it's actually 200. Because if I cut it back here at 3 meters, I don't have a height of 200 newtons per meter. And if I cut it way back here at 1 meter, again, it's not that. So this is one of those situations where I have to write an equation for my line, mx plus b. So starting at the left, moving to the right, we're going to kind of put our little coordinate system right there. I'm putting it up above this because this area has been taken care of by a different equation. So our y-intercept is 0. Now we have to deal with our slope, and slope is rise over run. So if I look at the whole picture, I have a rise of 200 newtons per meter. And if I look at the whole run, it's 6 meters. So I get a slope of 33.3. When I write then an equation for my line, x. Okay, so with a uniform load, it's just 200 newtons per meter across. When we're dealing with a linear load, we have to write an equation for the line. So now things are going to be pretty easy. Let's sum our forces in the y direction, and we get a positive 800 minus, okay, base times height, minus 1/2 base times height, minus shear equals 0. Again, positive behavior, but when we're summing forces and using equilibrium, we are calling up as positive. So this is actually showing down when we look at equilibrium. So shear equals 800 minus 200x minus 33.33 over 2x squared, and the units on that are newtons. So that's our shear equation. Now let's sum the moments about our cut. And again, going from left to right, I just find it's easier to always sum it about the cut and just be consistent so that I have a pattern and I'm more likely to get correct answers because you all know me. So here we go. We are going to have a negative 800 newtons times x. That's our force times moment arm. It's creating clockwise rotation, so it's negative, plus, okay, base times height, x times 200. And then the moment arm of my rectangle. So the centroid is just the base divided by 2. That's my moment arm. So as my base gets bigger, my moment arm gets bigger, and it's going to be half that length. Plus 1/2 base times height, and its moment arm. Where is the centroid of a triangle? Well, we know that it's 1/3, 2/3 ratio. So this centroid coming back from my x is x over 3 plus moments equals 0. So now we're going to take a negative 800x plus doinka doinka 100x squared minus, oh gosh, 3.33 over 6x doink 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 cubed plus moment equals 0. So my moment is, we'll move all this stuff over. Holy cow, that's a plus. I can't carry anything down. Is positive 800x minus 100x squared minus 3.33 over 6x cubed Newton meters. There is my handy dandy equation. So now what we're going to have to do is we are going to have to go back and we are going to have to write these equations by our shear moment diagram and then start plugging in values of x for our solution. So let's get started. You guys pause it, start graphing things as you can, and then come back, turn it back on, and check your answers. So I'm just going to do a quick sketch right over here. I know that I have 800. I know that I have, gosh, what was that value? 1,000, I think. And I have something that looks like this. Okay, and I have one length that we'll be working with. So I have shear, and I have moment, and you guys can't see diddly squat. So I'm going to move this up like so. Okay, so let's look at shear. We have 800 minus 200x minus 33.33 over 2x squared. When x equals 0, my shear is 800 newtons, which is perfect. I'm really hoping that when x equals 6, my shear is negative 1,000. We'll learn about how to guess all of that stuff on some of our next videos. So we have 800. We have a 200. 6 times. We have a 33.33. 2 divided by 36 times plus and plus. And perfect. Close enough. Negative 1,000 newtons. So I'm starting over here at 800. Which is nice because I can see my reaction is actually pushing up at 800 to start this curve. And I end over here at 1,000. It's a negative 1,000, which is great because I can see I'm going to be able to close that curve with that 1,000 that I have. So I have to connect from here to here. And if you don't know how to connect, if you don't know what it's going to look like, then come back in here and say when x equals 1. When x equals 1, then I have 800, 200 plus 33.333, enter, 2 divided by, negative, plus, so I get that shear is 583. So I could actually draw this out to scale, and at 1, I'm kind of down here to 583. Okay, the other thing I note is I have positive shear and negative shear, so that means at some point I need to figure out where my shear equals 0. And we can do that by setting our shear equation equal, whoops, minus 33.33 over 2x squared. And many of you have calculators that will solve for roots of an equation. I know that mine does, but I'll be honest, folks, this is, I don't know, from the late 80s, early 90s. And I don't remember how to do that, and I haven't taken the time to remember myself. So I actually go to Wolfram's. It is the best website for math things, and you can go to the algebra in there, and you can do all sorts of cool things, but one of the things you can do is actually put in equations, and it will solve for the roots. Okay, the roots are where we equal 0. So when I put this into Wolfram's, I found a value of, it's really cool because you can graph things in 3D. It's just, I don't know, it's super cool. I found that the roots were a negative 15 point blah blah and a positive 3.165. Okay. And so that's not even in my range. I don't need to worry about that. This is the value where I actually have 0. So if this is 3-ish, this is about right here. So this distance is 3.165, slightly off center. So I know that this is going to look something like this. And you can graph that out if you want to. This is where my shear equals 0. We could actually go back and we could plug in x equals 3, and hopefully we get the shear that we found on the last assignment. Now I'm going to take my moment equation, and I'm going to plug in x equals 0, and I get a moment equals 0, which is perfect because I can't have a moment at this reaction. It doesn't hold a moment. Rotation would occur, and I don't have an applied moment here. So looking ahead, I'm really hoping that I get a 0 here. I also know that where I have this value of 0, I'm going to have a maximum or a minimum. So it makes sense if I can start at 0 and somehow do something. So let's put in x equals 6, and we should find that our moment is, you guys calculate with me, assuming I've done everything right. Back. Plus, perfect. I get a moment of 0. And now I need to calculate where that maximum occurs. So when x equals 3.165, moment equals, see, this class really is just all algebra. And if you knew how important this was, like in 6th grade, I mean in 8th grade when you took algebra, you might have paid more attention because there's a lot of stuff that my younger kids are doing at school that we are kind of doing the same thing. This is like practical application of math, which I think is kind of fun. But I know I'm a little bit on the weird side. Sorry, I'm trying to calculate this stuff out. Times plus 1354. If I did my math right. Okay, if I didn't, just figure it out yourself. So 1354. Okay, what is it going to look like? Again, I can plug in values in my equation to sketch it out, but I know if this is a 1-degree curve, and I've kind of seen that I'm integrating under my curves, if I'm at 2 degree, this has to be a 3 degree. I also know based on the shape what this guy is going to look like. If you don't know, again, go back, plug it in. Okay, so fancy schmancy. I will see you on the next problem. Thank you.